Okay, so let's start. Last lecture we got up to, I think, around about this slide here, where we were talking about inventions of the 20th century, 21st century that include sort of quantum mechanics, and we were saying how basically there's not really actually that many inventions that use quantum mechanics. There's a few examples like MRI machines and lasers and things like this, which I think are sort of closest to using quantum mechanics, but there's actually not really that many. So essentially, I know what's going on here. Okay. Yeah, so a lot of the inventions use classical physics, and really this field of quantum information or quantum information technology, it's a field where we are trying to explore what kind of new inventions you can use with this kind of quantum physics, because most of inventions are based on classical physics, but if we have a whole new set of laws that we can use, then we should be able to maybe do more things than what's available with classical physics. Okay, just wanted to check. Yes. All right, so that's the kind of field that I'm personally researching in. And actually, it's quite an interdisciplinary field. So I'm a physicist by training, but actually there's a lot of people from computer science, from maths, also engineering. So all kinds of people are really interested in this kind of area now, and that's actually one of the real sort of kind of fun things about the field, because you can talk to people with very different backgrounds and kind of all talking about the same thing. Here are some examples of quantum technologies that people are really thinking about today. And these are just sort of kind of very broad categories. These days there's sort of more and more ideas that people are thinking about, but in a way these are maybe the sort of the traditional sort of subfields that people are thinking about. So first one is quantum T-distribution. So this means basically doing secure cryptography, right? So we're all familiar that cryptography is actually gaining much more importance these days, particularly with the internet, because everybody wants to communicate with each other, and then to do it securely is now really a really important issue. So it's not just with banking. I mean, now everybody's really worried about privacy and people looking in on your messages. You don't want Google to be harvesting all your information, making kind of clones of yourself, so that they already can predict what you want before you even know it. Things like this. People are starting to get very worried about these kinds of things, and so cryptography is now becoming immensely important kind of topic. And basically, cryptography is based on really methods of sort of encoding things, and really all these things are, in principle, you can break them if you had a powerful enough computer. So for example, many of these cryptography schemes are based on encoding things in some way, so that, for example, if you use like hash functions, then it's easy to go from, say, your plain text into some encoded message, but the reverse is very difficult, right? And so this kind of one-way nature of encoding things is often what's used. But if you had a powerful enough computer, you can actually break these. So a lot of these things, the security of the cryptography is actually based on the fact that, okay, well, surely nobody has a computer that is, a million times faster than the fastest computer, or a billion times, or something like that. So basically the state-of-the-art computers, and you go, well, okay, if you make the problem so that it would take 1 million years to solve on the best computer available today, then, well, effectively it's secure, right? But it's kind of based on what's available, and probably that there's not any computer that's that powerful, but what would be even better is if you could make some cryptography which is like fundamentally unhackable. So, by the laws of physics, you could not break the codes. And so that's basically the idea of quantum cryptography, to make codes that are impossible to break, like by the laws of physics.
So how does that actually work?
Yeah, so I think we have to talk about that towards the end of the of the course, because yeah. So I'll make sure we'll include that, I guess. But roughly speaking, it's to do with how measurements are made in quantum mechanics. So the way that you sort of do it is you encode it in a way such that when you read the information, you kind of you can't really properly extract it because of like fundamental limitations on measurements. So quantum mechanics is different to classical physics in terms of measurements. Like, so if you have something classical and you've got like 1 0 0 1 0, you take for granted, well, I can just read that, right? So everybody can read it. Reading it doesn't do anything to it. Like, reading is it's a passive activity, right? But quantum mechanics, actually reading it does something to it, because it's so sort of fragile, if you like, that actually reading it sort of messes it up somehow. And you take advantage of that in these schemes, so that when you read it, you know that somebody's read it, right? So if a message is going between two people, and then somebody has read it in the middle, you know that's happened, because you can see that in the state. So these types of schemes are like, if you find that somebody is reading it, then you just go, okay, somebody's read that, let's get rid of that, we're not going to use that, and then you keep on doing it until you get a clean connection. Something like that. Okay, so that's cryptography. Other things are like quantum metrology. So these are doing like sensitive measurements, and of course, that's quite a important topic. Well, science-wise. So this picture here is supposed to be like pictures of some gravitational waves. So these are extremely small fluctuations in space-time, and probably you would have heard of a couple of years ago there's a big experiment where they saw this for the first time. So actually they didn't really use so much of the techniques of this field, but now they're starting to do this. But the point is that these measurement devices these days are getting so sensitive that they're getting down to like the fundamental limit of how accurately you can measure anything, right? So getting down to the level where you're seeing, there's noise. There's always noise in a measurement if you look closely enough. But the noise is now coming from quantum mechanics. And then so that's a noise you can't really do anything about, actually. That's nothing got to do with your measurement device not being, like a good enough measurement device. That's like a fundamental kind of limit, because that's in the system that you're trying to measure in the first place, right? So now the measurement devices are that good, and so basically the idea here is to then say, okay, fine, well, we've reached that sort of quantum limit. how can we improve that by knowing the quantum states of things, and maybe we can even go down below that limit by doing special kind of tricks, by understanding the quantum aspects of the measurement. That's one direction. Another thing is these quantum simulators. It's a bit harder to sort of explain in sort of kind of normal language, if you like, but essentially this is more like material science, which doesn't sound really sexy, but fundamentally understanding how materials behave, like new materials, you do need to understand them at a quantum level, and what these things are like making sort of, say, artificial crystals or artificial materials kind of from the atomic scale up, and then that way we can sort of understand things much better. So that's sort of the gist of that one. And quantum computers is probably the one that is most famous. So of course there's quantum versions of computers that you can maybe do new types of calculations that you were not able to on classical computers. So by the way, in our field we call these classical computers, like as if they are like ancient devices, and well, that's a way to distinguish the regular computers from quantum computers. So in quantum computers, or people think that, to some extent people know that you can do certain types of problems much faster than on a classical computer. So some people have the misconception that you have a quantum computer and then you can do everything faster. You can run Word and Excel and Minecraft, anything. It runs really fast. It's not really true. Actually, classical computers are really fantastic things, and I don't think they will become obsolete by quantum computers appearing on the scene. But certain types of problems, classical computers can't handle very well. So those things like that I said, like Excel, Word, these things run fast enough, and there's obviously no point. But certain other types of problems are, just really difficult because, as soon as you increase the problem size, the computational time just explodes. So usually things like optimization problems are like this because basically there's a lot of different combinations, and the combinatorics just get so bad that finding like an optimal solution becomes really very difficult. So this is sort of an ongoing topic of research in the field, but some people claim, and it's an ongoing topic, but some classes of optimization problems people think you might be able to do faster, and some specific problems people have shown you definitely can do faster, and these are problems like factorizing numbers. So if you want to factorize numbers, and actually that's quite an important kind of task, because that's actually what a lot of cryptography is actually based on. So you could actually use it to break codes, and it's like exponentially faster than a classical computer. So these are the broad kind of categories, but more recently there's been all kinds of developments. Like people think you can apply quantum computers to machine learning. So there's this whole subfield of quantum machine learning that's been very popular in the last 5 or 10 years. Other things are like quantum finance, so applying quantum computers to finance. Again, this is actually an optimization problem in the end. So people are looking for all kinds of applications. Okay. So I just want to sort of highlight a few of kind of, flashier experiments that have been done in this field. So one topic actually that is really taking off in the last few years is quantum communication. So what does quantum communication mean? It basically means like that you are, obviously communicating, but you have some kind of quantum mechanical communication between two parties. So instead of, say, one person, so traditionally in this field we call everything like Alice and Bob. So these are two people, maybe in two different places. So Alice wants to communicate with Bob, who's maybe over there. Classically, what do you do in communication? You just send ones and zeros, right? So you just send ones or zeros. In a quantum communication scenario, then you would be sending actually quantum states from Alice to Bob. And actually not only that, you might even have entanglement between Alice and Bob, and then you can do all kinds of fancy things. There's been a lot of work recently on maybe building things like a quantum internet, so some kind of world-spanning network that's fundamentally based on quantum mechanics rather than the present internet, which is classical. So towards this, these are some sort of major sort of breakthrough experiments. So when I first saw this, I thought this was pretty mind-blowing what these guys did. So this is a group in Austria. So there's a guy, Anton Zeilinger. He keeps on missing out on the Nobel Prize, but a lot of people think that he'll get the Nobel Prize soon. So he did some experiments where they perform teleportation between kind of two islands, and these islands are off the coast of Africa. So this is Morocco. For some reason I got the Japanese version. So these are two islands off Morocco, and they sent light basically just across the ocean, 143 kilometers, and they did this experiment where they could teleport a state of a photon from this is where you input some quantum state, and this is actually where you create sort of entanglement, and then finally this is where the desired state is teleported. So it's sort of like this is your input, and you do some stuff with entanglement, blah blah, and then your state comes out here. So you might be wondering, why did they do it on these islands? Did these professors want to go on a holiday and have go to a nice island and do the experiment there? No, there's a good reason for them to actually go there. So if you actually think about like the curvature of the Earth, so I think over 143 kilometers, actually the Earth is already curving so that you can't even get a line of sight. So one thing is that on these islands, these are actually yeah, exactly. Yeah. So I think they're probably like volcanic or something like that. So there's like kind of huge islands here, so you can actually get over the Earth's curvature. Obviously, the air should be quite clean, so you need a nice kind of clean air. So it looks pretty clean probably there, right? It's in the middle of kind of the ocean. And also in practice, when you do these things, essentially, you're sending like one photon, and it has to make it 143 kilometers, right? So, of course, anything that's in the way, absorbing it, will block it. But in practice, basically, you need a telescope to do this experiment. So you basically need a telescope, I think on the receiving end, this island here, like, and I don't mean like thing that you have at home, I mean like an observatory, right? Yeah. So you need to have an observatory that's on like a mountain. They're actually often on mountains anyway, but and it needs to be sort of somewhere clean, and it needs to be somewhere sort of so that you can 140 kilometers or something away. So there's probably not really that many places in the world to do it. So that's why they did it there. So that's quite impressive. But actually, recently in China, things have really taken off with this. So that kind of experiment is already impressive enough. But a couple of years ago, so this is already after I personally arrived in China. I arrived here about 6 years ago, and they started to do these massive scale experiments, and probably you might have heard of it. Have you heard of it? These experiments? No? Okay. But anyway, this was like quite a big deal, and basically the idea is to do these types of quantum experiments, but from space, right? And so essentially the difference now is that instead of like shooting it through the atmosphere parallel to the Earth, you basically go all the way up to space and then back. And that's quite a good idea, because if you have the Earth, right? So I don't know about the scale, but actually, the atmosphere is quite thin. It's only, I don't know, 10 or 20 kilometers thick. Right? So really, the atmosphere is the thing that really messes up your experiment. So those guys that were doing it from those two islands, sort of doing something like this, right? So it's going through the atmosphere like this. But if you go to space, well, obviously there's no air there, so nothing to block all the photons, no problems with scattering. So you could go into your satellite, you can go straight up and then down here, and then the amount of air that you're actually going through is not so much, right? So I said it's only maybe 20 kilometers thick, right? So it's just 20 kilometers through on the way up to space, and once you're in space, it'll just go forever almost, right? And then 20 kilometers on the way down. So this is like obviously, but people had in mind that this was a really good idea to do it, but of course it takes a lot of money to make a satellite, right? In terms of an experiment, this is a pretty expensive experiment, because you've got to make a satellite, you've got to launch it into space. I mean, this is sort of like $1 billion program or more. Right? Yeah. Well, this is why everybody gets very excited about space, because it's quite expensive, right? I mean, I'm joking. I mean, it's exciting because, well, it's space. So just a little bit of, I guess, a backstory, because I happen to know some of the people that were thinking about this. So I had quite a good collaborator of mine called John Dowling. He actually passed away sadly last year, but he was involved in thinking about doing these types of experiments. So the US were thinking about doing these types of experiments maybe a decade or maybe longer ago, and so Europe was also thinking of these things, but essentially they just couldn't really get the kind of the money together to do these things, right? And so really out of nowhere, basically just China kind of came along, wiped the map in terms of this kind of approach, because essentially nobody could really put it together, and these are really now groundbreaking experiments that are really being done right here in this country. In fact, the people that put together the satellite are just in Minhang campus of University of Science Technology China. And so had a look, visited there, and saw some of these results when they were first coming out. And so, yeah, so there's really actually exciting things that are happening, actually right here in the city. So, it's calling me now. Well, okay, and then now if I digress even more, so, where we're at is now kind of the point that, a lot of this technology is, China is the only country in the world that has these technologies, and a couple of years ago, Donald Trump signed a new quantum initiative in the US to really boost the kind of research in quantum technologies. And I'm pretty sure these experiments really had quite a lot to do with it, because these, basically, this is sort of laying the groundwork for a future quantum internet, right? So if you have the quantum internet and all the technology is being developed in another country, then this starts to really get a lot of people, kind of anxious about the nature of quantum technology in their own country. And then so this has really turned into actually like a huge kind of a boom now in this field, because a lot of people really are trying to do anything with quantum technology. So now you're getting at the point that, quantum technology, everybody's making quantum startups and just trying to put quantum in everything. It's a little bit like the Bitcoin bubble, where you just put in like Bitcoin or blockchain and everything, and then, getting like...
Yeah, I know, you see it all around the internet and stuff.
Yeah. So, anyway, so that's kind of the status of the field now. It's really, I think, quite an exciting time to be doing it, and to be doing it actually in this sort of city, this country, is I think it's really kind of a pretty cool thing. So, okay, so getting down to earth a little bit, but even this is not so down to earth. So that's quantum communication, but what about things like quantum computers? So quantum computers, of course, are kind of a different kind of hardware. Of course, these are generally more like computational devices, but it's still not really clear what is really the best technology to build these quantum computers out of. So if you think about how regular computers, classical computers started, arguably the first type of classical computer was things like the Babbage engine, right? So you have gears and these types of things where sort of programming it with levers or something. And then you go from gears, and then of course the first types of computers before semiconductor-based computers were based on more sort of electromechanical type devices, relays and things like this. And then of course the breakthroughs, transistors and integrated chip technologies and miniaturization. That's where we're at now. So in a similar way, I think quantum computers will go through different phases of technological sort of metamorphosis. So people are researching in parallel various types of platforms where you could do quantum computing, and maybe these are sort of 5 best known ones. So I guess starting from the top there. So maybe one of the sort of earliest types of systems where you see these types of quantum behavior is actually quantum optics. And so that means basically you use light, so light like here from my laser basically, and you use sort of optical circuits in order to create your sort of quantum computer. So the things that actually hold the information are like photons. So this laser is shooting out a lot of photons out of the laser, and in each of those photons you can encode some information into it. So things like the polarization of the photons, or some other things. There's various ways of doing it, but you can make sort of circuits using basically optics, right? So optics is good because actually light is one of these things that it doesn't interact with anything. You shine it on something, and then it basically almost passes. Well, it kind of doesn't. Yeah. It doesn't have charge, so there's no kind of electrical force. You can't really apply any magnets to it. So that means essentially, it'll basically keep on going, and the information is actually pretty robust to become corrupted. So it's actually one of the first types of systems that people really looked at, kind of quantum mechanically, and actually a lot of the people that are working in this field originally come from like quantum optics. So a lot of the kind of basic ideas originate from quantum optics and then migrated to other systems. So that's kind of maybe where a lot of the origins lie, and definitely a lot of people still do that. Yeah, a couple of my guys that I knew from university, so I'm from Australia, and actually Australia is quite strong in this quantum optics, and yeah, there's a couple of them that are now kind of got big research groups in this kind of area, even making startups based on this kind of technology. So you make these kind of waveguides and build circuits like that. So that's one way, but maybe the leading way that people are thinking today, so this is probably the number one choice today, which is superconducting qubits. So in this case, you make the whole thing out of superconductors, and again, you make these kind of circuits out of superconductors, and well, done in the right way, you can build qubits out of them, which is like the elementary operation.
So the superconductor, it conducts photons? Or?
No, so superconductors are essentially what they have still electrons. Yeah.
Yeah, so they still conduct electricity? Or?
Yes, yeah, they conduct electricity.
So they're just like regular stuff, only smaller and with superconductors?
Yeah, actually not exactly, because the kind of thing that you do is, so the superconductors inside, actually they're made of actually pairs of electrons, and so somehow the electrons like to pair up. I won't get into that, but it just does. That's part of the magic of why they're superconducting. And then you make these circuits so that you make these sort of oscillatory circuits, so that these electrons like to kind of oscillate. It's almost like they're in some kind of bowl. And then essentially what happens is that these oscillation modes become quantum mechanically quantized, and then you use that as the level. So actually there's not really that much electron flow, so it's not like there's a lot of electrons flowing around everywhere. It's more like they sort of vibrate, and then you use some of these levels. I mean, it's a bit hard to explain, but yeah, it's sort of more like what they do. Other types of technologies are things like diamonds. So diamonds not just pretty things that you can use for jewelry or or any other things. Diamonds have these defects in them where, of course, so diamond is made of carbon, but occasionally one of the carbon atoms can be replaced by a nitrogen atom. And if you remember from chemistry, carbon has like 4 bonds, but a nitrogen only has 3. And then so there's a kind of a missing, sort of atom that's there. And basically this combination you can use as some kind of qubit. So it's like you can store information in these kind of defects. So it turns out that they actually work very well. Somehow this kind of crystal structure protects the information really pretty nicely. Other things, things like you make various structures out of semiconductors, or so-called ion traps. So ions, of course, they're just charged atoms, and once you charge them, you can kind of fix them in space. So a neutral atom, you can also do it with neutral atoms, but there's a good way of kind of trapping single ions so that they're kind of levitating in air. And you put this whole thing in a vacuum, and then all these sort of chips are just the kind of machinery to kind of make them float in particular positions. And then you start shooting lasers at them, and then use them as kind of qubits. So these are all pretty kind of fancy ideas for technology, but and actually, so we are also aiming to build a kind of quantum computer right here. Well, in our
around here, you mean?
Well, actually, my lab is at ECNU Minhang campus because there's nowhere to put a laboratory in this building. Maybe if we move to the next campus at Jiantan, maybe our lab could be there, but still under negotiation, so I don't know. But we have a kind of a pretty original scheme of also making a type of quantum computer, and our one is more, it's most closest to this ion trap one, but we're using neutral atoms, not the ion, so it's a little bit like that one. But well, I could tell you all about it, but it's
very interesting.
Yeah, kind of a completely new approach to, well, firstly, a totally new platform for making quantum computers. Also, our main selling point is that the main problem with all these things is that there's always noise that comes into it, and dealing with errors is a really huge problem because they're very sensitive things that where the information can be corrupted easily. So what we're doing is to use like ensembles of atoms where there's a lot of duplication of the information, so that even if you lose a few atoms here or there, it doesn't really matter, you still got the information. And so it's a little bit like, more like what you do classically in a way. So it's like, you have a macroscopically sort of quantum object which can store a lot of information, so that, as I said, even if there's a few errors, it doesn't get destroyed. So if you want to know about that, we can talk about that. But so that's the kind of technologies that are there that people are thinking of today. But maybe the one that most people would agree, as I said, is the leading one of this superconducting computers. This is the one that IBM and Google and a lot of companies are now pursuing, and the one that's making a lot of breakthroughs at this point. Well, I personally hope that it will change, and then my particular platform will be the eventual winner, but of course, you never know. So we'll talk about this more, but so why is a quantum computer faster? So the kind of explanation, which is often quoted and one that increasingly everybody hates to hear, is this one. So basically, in a quantum computer, what happens is that well, what is a computer? Firstly, well, you have some input and some algorithms and some programming, and spits out some output, right? That's basically what a computer does all the time. Now, of course, the point in a classical computer is that you can only put in one input at a time, right? So if I've got my Instagram filter, I can only put in generally one photo at a time, and just processes it and does another photo, unless you've got two computers, of course. But if we're just talking about the one computer, it will process one input at a time. But in a quantum computer, because you can have this aspect where things can be in this superposition, and we talked about this, if you remember, when you have a wave. I think waves can be sort of two places at once. So we had that, like a particle going here, and it could go around. It looks like an eye, but nothing go to an eye. You can go around the top of this circle or the bottom, and you can do it sort of at the same time. Yeah. So this is one feature of quantum mechanics where you can sort of have things in sort of two states at the same time. So the idea then is to, in a quantum computer, you can like stick in all these inputs like all at once, and then it will actually calculate the outcome of all that kind of all in parallel. And it's not just a couple of different inputs, and it's not like a couple of photos that you can put in here. It's like potentially an exponential number of these inputs that you can put in there. So this is what makes it, well, this is what kind of explains where the speed up can come from. But actually, it's not really quite as simple as this, and this is why I said that a lot of people hate hearing this explanation, because actually, this is not a recipe for making quantum algorithms, because what happens is that, yeah, you can do this, but then when you measure it, actually you only get one of these outputs, and it happens randomly. So you need to be smarter than this, actually, to make a good quantum algorithm. So this is sort of hand-waving or plausible explanation of why quantum computers might be faster, but it's not actually a recipe for how to make it faster, because actually doing that doesn't work. That's well, that's that. But we will talk about actual algorithms that do run faster, and then you can see exactly why they should be faster. Yes, and I mentioned IBM and Google really jumping into this race and getting involved in this quantum computing research. And IBM and Google, they're pursuing this superconducting qubit technology. Microsoft also on this race too. I think mainly because they got this guy, Michael Friedman, and I think he's like a Fields Medal winner or something, and he's now at Microsoft, and he's very interested in like these topological quantum states, and so they're pursuing this kind of technology, which is actually not in the list of 5 main technologies. It's actually even more obscure, but well, somehow it's convinced Microsoft to pursue that one, so that they're going for that one. But a lot of the other, these are all other superconducting qubit technologies. This is well, was one of the early startups. Well, actually, the earliest startup is this D-Wave. I don't know, have you heard of D-Wave?
No.
Yeah, okay, yeah. So D-Wave, kind of interesting story. So D-Wave was the first quantum computing kind of company, and so they did this really early. So that's 2,000 qubits. When did they start? I don't know. Could be over 10 years ago. But like now, I said, everybody's jumping in on the startup and making quantum companies, but it was not always like this. In fact, so when D-Wave started, they were the first company. They did it like much earlier than anybody else, and I believe it was actually founded by this guy called Geordie Rose. He started it. He was the founder of this company, but I think actually he had no real background in quantum physics. I think his background was in like wrestling or something. Yeah. So he went from like a professional wrestler or something like that to founder of a quantum company, and I think he's Canadian. So this was a Canadian company. But I mean, I think you have to hand it to them for they were really right on the money for doing this, and they were laughed at, and people were so skeptical about this company for a really long time. But somehow this guy, or maybe it's a team of them, picked actually the right technology, this superconducting qubit technology, which is now what Google, IBM, all these guys are doing. And they also chose a very smart way of doing the quantum computing, where it was really actually quite difficult to tell whether it's actually working or not, because it's kind of a way that people are very interested in. It's actually solving optimization problems, and so it's actually a really important problem. So if you could really do it faster, it's actually super important. But it's actually also really hard to work out whether it's running correctly. And so it's, even though I think at first people were really kind of laughing at them, now they're kind of a little bit more respected, and actually I think in a way they, I think, deserve a bit of credit, even if maybe the technology of the other companies now are much better. So I think still now they have the largest number of qubits, so they've got like 2,000 qubits, but it's just quite difficult to test whether it's really running properly or not, because the whole point of these quantum computers is that they're faster than regular computers, so you can't even check whether it's really running fast, or it's at least quite difficult, so it's actually a serious research problem. Yeah, and yeah, this is another company. So actually, these days people are really starting to, prepare for the new sort of quantum industry, and so in my hometown of Sydney, there's this new thing that's being created called the Sydney Quantum Academy. I'm not trying to plug them or anything like that, but what this is it's like a new type of, essentially a school to train the next generation of quantum physicists to work in these types of companies. So, people are already really thinking in this way that, it's like a kind of an employment path, right? So going from kind of obscure academic research to now, there being training centers to train the next generation of quantum engineers. So, it's really kind of a remarkable change that's only really happened in the last 10 years or so. Okay, all right, so it's getting a bit slower than I thought, but so in this course, so this is not really typical of kind of what we'd be doing in this course. Actually, this is a much more nuts and bolts type of course, so it's not really a humanities or this kind of course. It's actual serious physics. So I'm just sort of whetting your appetite, if you like. So what I want to sort of achieve in this course is to just from kind of basic knowledge of, actually sorry, this slide is old, so I don't even do very much calculus in this, so it's really just vectors. So I want to teach you about quantum theory, basically how it works, and also take you from that to learning about some of these quantum technologies. And I think I'll mainly focus on quantum computing because I think that's it's the most sort of, in a way it's the most exciting, and it's also the most sort of easiest one to sort of start with because it's a little less sort of abstract, or it's a bit more self-contained than some of the other topics. So you can really sort of see how computation is being done in quantum mechanics.
And also it's like your field, right?
Yes, yeah, but I do sort of everything. I think the only one that I don't really do is like quantum cryptography. So probably I do everything else except for cryptography. So, but maybe we can talk a little bit about cryptography too. So. Okay. So I think that's the end of this one. So I think I'll move on to the next slide. I've only got 10 minutes, but any questions?
Not so far.
Yep. Okay. Everything okay, Elin? You can hear? Okay. Okay, great. All right, so let's move on to the next topic. Okay, so so the first kind of real topic I'm going to talk about in this course is this early history stuff. So when you first learn quantum mechanics, like as a physics student, this is actually where you normally start. So you talk about how quantum mechanics came into being, and sort of like why we need quantum mechanics, and so forth. Actually, the way that I'll sort of describe quantum mechanics is actually not really going to follow this kind of early history idea. And when I was learning this quantum mechanics, you think like the first stuff that appears is this first stuff that you need to know because it's probably the most basic. In this case, this is not, I would say. So I would say that this early history, you should think of it more like just sort of a history lesson, and then not as the fundamentals of the topics. That will sort of come sort of after this, when we learn sort of linear algebra, complex numbers. This stuff is the fundamentals, and actually learning the early history does not really help you very much in terms of doing quantum mechanics, because
so it changes over the time.
Yeah. So the way it looks like in the early days and the way it looks now is like so different that it's almost like not related to each other. So, well, I don't know. Maybe learning a bit of the history is still a little bit interesting. So, I'm going to take you through a little bit of a journey through time. Starting from pre-quantum mechanics days. So, of course, quantum mechanics was sort of invented in the early 20th century. So prior to that, there was only classical physics, and physics originally started from things like thinking about stars and planets and things like that. So one of the early types of topics that people were looking at were planetary orbits, and so people like Kepler were formulating their laws of orbits. But really kind of the real very quantitative and fully universal type of theory came with, of course, Isaac Newton, and famously he made Newton's laws, three Newton's laws, and whole sort of mathematical toolkit. So he's also a very good mathematician as well. But maybe this stuff I'm sure we've all heard about, but maybe what's interesting is the kind of worldview of a physicist in this time, because if you look at Newton's laws, these are completely deterministic equations, right? So if you know your initial condition and your initial velocity, then you can use Newton's laws to propagate everything through time, and you can work out what everything's going to happen just from that. And so, there are questions of kind of determinism in this, and even links to sort of philosophical questions. So, if we can predict everything, are we just living out some animation where everything is sort of predetermined, and actually I have no free will? I'm just kind of rolling along with Newton's laws, and I'm just playing out my whole life, and everything is actually determined. Right? So, if you think classical physics is the ultimate reality, then you basically you're forced to conclude that essentially everything is predetermined, and you are just playing things out. But as we'll show, quantum mechanics is a probabilistic theory, and there's an element of probability that you actually cannot really remove from the theory. And so actually there's really a fundamental change of how you kind of view the world, because in classical physics everything is determined, but in quantum mechanics everything is random. So it's quite a opposing kind of point of view. So that's an interesting problem in philosophy, but it's also one of the reasons why quantum mechanics is kind of so interesting. So okay, back to the history lesson. So things like light, Newton also was thinking about what is the nature of light, and around about 1800, people discovered that light indeed was a wave. Actually, in Newton's time, so Newton was alive more like 100 years before that, people were not sure if light was a wave or not. In fact, Newton, I think, thought that light was made of particles, and in a weird way, even though 100 years later he's almost convincingly proved wrong, definitely this is light as a wave. Actually, geniuses have a way of being correct even when they're wrong. So, in the end, actually Newton was even right that light was a particle, because actually light is made of photons, and photons are particles, and there's this wave-particle duality. So there's actually it's a wave and a particle at the same time. So in a way, it's interesting how just some geniuses are just never wrong. And Maxwell's theory of electromagnetism really quantified this kind of nature of light, electric fields, magnetic fields, and around the end of the 19th century, Lord Kelvin, whose the temperature scale is named after him, essentially said that there's nothing new in physics that's left to be discovered, but all that remains is for a more precise measurement. So he thought essentially physics was kind of dead in a way. All the discoveries were all made, and you can, in principle, predict everything. Maybe you just have to look at more complicated systems or precise systems. So he could not be more wrong, because physics is actually alive and well still today, and in fact many problems that people still don't understand. But around about 1900, the most biggest problems in physics look like almost some details really, but actually this was a Pandora's box of of things which, as you look deeper, it became stranger and stranger, and this was really the start of quantum mechanics. So there were these three phenomena that people couldn't really understand very well around about that time. And I'll just go through these three things. And so the first one was this black body radiation, ultraviolet catastrophe. And what this is talking about, and again, this is why this is not the way to learn quantum mechanics, because this is such an obscure thing, and it's like such a weird phenomenon, and it's like, why am I looking at this? But anyway, historically, this is what happened. So if you look at the spectrum of something that is, say, hot, so obviously if you make something hot, it glows red, right? And it glows red because as you increase the temperature of something, there's this kind of characteristic spectrum. So this graph is showing you what frequency light, or color light basically, is coming off this red hot object. So this is the wavelength of the light, and this is how much light there is coming off there. And when you heat something up, what tends to happen is that in this curve, this is the intensity, and that was the wavelength, right? So wavelength. So when you heat something up, what tends to happen is that there's this characteristic kind of curve, and I should get this right. So this is something that's at sort of high temperature, and I think at lower temperature it sort of looks something like this. It sort of shifts more to the right. And so the reason why things glow red is because our eyes can only detect light in some fairly limited range of wavelengths, right? So we can only see light that's from about 300 nanometers to maybe about 800 or something nanometers. So we can only see light here. So when something gets hot, this curve is moving like to the left here, and there's more and more light, and this side is red, right? And this side is violet. And so there's more and more light on this right-hand side that you can sort of see, and red is the first light that you can start to see it. Right? There's more red light than violet light.
So it's like when it's really like torching, it becomes like a bluish color and the white.
Yeah, I think there's always more red light, because I think what happens is that as things gets really hot, I drew that badly, but I think there's always more red light. So things always tend to look a little bit more red than blue, unless you've hit like infinite temperature or something. But yeah, definitely there's more of like blue light also coming off. But things, yeah, I mean, when you heat something up, it looks like red at first, and then it's like more like yellow, and then it's like white, right, later on. So it becomes white because you see colors, all the colors come off all at the same time, like a old-fashioned light bulb. Yeah. So okay, so yeah, that's right. So what's the problem? So that's what you see when you measure it, but when you try to calculate it, what you get is something more like this curve, where you predict actually there should be more and more and more light coming off in this short wavelength region. And I don't want to really get into it so much, but the reason why is because for things with short wavelengths, there's actually many more different ways that you can have short wavelengths rather than long wavelengths. So if you think about like a piece of string tied at two ends, there's really only one kind of long wavelength that you can have. But you can have like actually many different types of like short wavelengths. And this is actually even more true if you've got like a 2D, two-dimensional or three-dimensional thing. So there's actually many more different shorter wavelengths. So if you heat something up, you would think that there'd be all different types of short wavelengths coming off it. But actually, there's actually no short wavelengths coming off it. So the theory predicts something, catastrophically wrong. So you would expect there's like a lot of short wavelengths, but there's actually none. So that's why it's called the ultraviolet catastrophe, because the theory is catastrophically wrong. So a new theory was kind of needed to explain this. And there are two more things, but I think we should leave it there because it's nearly 3 o'clock, so we can continue on with this next week. Okay. And so the first homework is I've uploaded to NYU classes, and it's actually getting a little bit ahead of the lectures, but I think you can still follow it. And so it's the first homework is part of it is reading the kind of history of quantum mechanics by John Norton, and some I think you just make a summary, and there's a couple of other.
The cat, Schrodinger's cat.
Yes, that's right. Yeah. Yeah. So if you could do that and then hand it in by we can make the homeworks. So I'll set them on Thursday and I'll receive them on Thursday as well.
Tuesday's good, I guess.
Well, yeah. Okay. If you can hand it on Tuesday.
Okay. I think it would be like more time to look over it.
Yes. Yeah. Okay. All right. So see you next week.
Okay.